will give us pre-talk about F singularities, and then this afternoon we will have a follow-up with our research seminar, always by her.
Great. Yeah, thanks so much. So yeah, I wanted to just give a brief introduction of F singularities. This is by no means going to be everything you could know about F singularities. So maybe I'll point to some references later. We will be a little bit biased in that we'll end up focusing on something called F purity or F splitting, and then talk about that pure threshold, because that's what's going to show up in my research talk later. Okay, so what's our setup? So R will be a commutative ring, often Noetherian, although we don't need to say it for now, of characteristic P. And probably all of you have seen this before, but just in case you haven't, what do I mean? I just mean if I take my identity, all my rings have identity. If I take my identity and add it P times, then I get 0. Great. All right, and what's special about rings and characteristic P? Maybe our key observation is that if I have the map from R to R, sending an element to its pth power, it's called the Frobenius map. Right, this map, which is usually very far from being a ring homomorphism, just in a random ring, is actually a ring homomorphism here. And maybe our point is that, of course, in a ring of characteristic P, if I think about taking two elements in R and raising them to the pth power, probably all of you have seen this before, but the point is that if I look at this and I write out, what I get, all of these intermediate terms are divisible by P, and so are 0 in my ring. So we get our freshman's dream, which makes this map into our nice ring homomorphism. All right. Because the source and the target are the same, we're going to do something where we're going to just add some notation to the target so that I can identify it. So we'll often write and this notation is inspired by geometry, but I want you to think of it as purely notation here. Okay, so what is this? This is just R. And I'm going to write its elements as half lower star of little r, where R is an R. So just think of it, it's exactly just a copy of the ring R, but I'm going to think of that. This notation is going to be it's the target of this map. All right, and maybe note, given any ring homomorphism, say F from R to S, we can turn S into an R module, right, by restriction of scalars. S into an R module by all right, so what do I want to do? I want to think of R acting on an element of S. So it's the module which is just, this has the same abelian group structure as S. And then if I want to act by R, this is just F of R times S. Okay, so we've got a ring homomorphism. So we can think of this copy of R, F lower star R, as an R module with a special R module structure, right? So we can think of F lower star R. It's just the ring R, but so this map will be injective whenever my ring is reduced, which is going to be the case that I am going to think about. So maybe, yeah, so maybe I should know is injective if and only if R is reduced. Yeah, that's a good observation. Right, okay, yeah. So when I say this as R, yeah, I want to think about R reduced. But yeah, in general, this is just, well, I can think of this as R either way. Potentially, I guess this isn't always injective. But yeah, I want to just think of, like, my source and target are still R. So I want to just think of this as a copy of R, and we'll write the elements as these, and then maybe, I don't know, depending, we won't land on all of R or whatever. But I just want to notationally think of this as this copy of R. Yeah, this is just to distinguish my source and target. So it's just a notational thing. All right, so we can think of F lower star R as an R module. Where, okay, so this thing is R as an abelian group. All right, and then I want to put this restriction of scalars on it using the Frobenius. Okay, so what is the action? Where for R in R, and I'm going to write them as, let's say, F lower star X in F lower star R. We write, so what does it do to these elements? Well, it applies my map and then multiplies. So this is raises to R to the P. All right, so this puts an unusual R module structure on R. All right, let's do an example. Pick a finite field and adjoin a single variable. Then note if I think of the module, the R module, F lower star R, what is this? This is actually a free module. All right, and what are its basis elements? So I need my 1. And then actually, I need every power of x up to p. And then once I get to, well, up to p minus 1, and then I can just multiply by x, right? Because if I multiply by this element x and R, I get x to the p. So all right, so I can view it like this. Maybe I should make a little comment on notation.
I think the audio went mute.
Am I on mute?
No, I cannot hear you. Yeah, something happened.
Right, for any power. This is going to be just the same exact construction where instead of sending r to the p, I send r to the p to the e for any power e. So I'll often use that notation as well. All right. One thing you might notice about that example is that that example is a finitely generated R module, right? Since in the example, this is finitely generated as an R module. We call this ring R. This was FP adjoining X, F finite. Okay, so F finite just means that if I apply Frobenius and then I look at the R module structure I get on that target, then I get a finite R module. And maybe I'll comment that most of the rings we care about will be F finite. Care about will be F finite, and maybe I'll say what I mean by this. All right, so for example, so if I think about maybe for fields, perfect fields are the ones that I care about the most, and they're F finite. And maybe I'll note that this includes algebraically closed fields. And also it includes finite fields. Okay. And then also, if I take any finitely generated algebra over an F finite field, then I get something F finite as well. Okay. And then maybe also things like if I localize an F finite ring, or if I take a quotient, or if I take a completion, I also stay F finite. Okay. So I'm going to change it to other one. Great. All right, I'm debating whether I should write this. Yeah, let's just assume from now on, because I think otherwise I'll try to mention when I need a finite, but I may forget to mention it. So assume from now on. Oh yeah, I will in a second. Oh yeah. Well, yeah, let's do that first. So I can play the same game here. Maybe what I can do is, for example, just adjoin infinitely many variables. And if I want, I could make it a field too. So I could adjoin round bracket infinitely many variables, and then I get a non-finite field. Okay, so something like that. Yeah, so now assume from now on that R is F finite. Okay, maybe what I want to Sorry.
Noetherian does not apply.
Noetherian does not imply a finite in general. Yeah, because I could take a non-finite field and just adjoin a variable. Great. So maybe I should say, roughly, maybe we've seen our first example of an F singularity. So F finite, maybe I would call some type of F singularity. But roughly, F singularities study either the Frobenius map. Well, I mean, essentially, they all study the Frobenius map. Or they study things like maybe F floor star R as a module. You can also think of it acting on different R modules, and you might study what it does to R modules, but we won't talk about that too much in this talk. Okay, and maybe we've already kind of hinted at why this might be important, because we noted that if R is reduced if and only if the Frobenius map is injective. So already it's telling us something mildly about maybe singularity or something we care about. All right, but maybe what's the main motivation? The theorem of Kuntz that says, let's say R is Noetherian and characteristic P. Then R is regular if and only if this F lower star R as an R module is flat. In other words, Frobenius can exactly pick up when we're regular, so it can tell us about smooth varieties. And we don't, maybe I should note, we don't have something like this in characteristic 0. Some like sort of nice, and well, in other words, we wouldn't know what to replace the Frobenius with in characteristic 0. Question? Sorry? No, we don't need to assume local. So yeah, we can always localize. Yeah, sorry. So when I say regular, I mean, I guess, I mean, every localization is regular local. Yeah. Okay. So maybe the first, well, I guess besides F finite, the first thing I want to talk about is F splitting. So maybe the question is, if the Frobenius can detect regularity, what else could it detect in sort of more restrictive cases? If we're not necessarily regular, can it detect sort of it detects some sort of singularities? The following definition. We say R. Oh, I should say P is Frobenius split or F split if this Frobenius map splits as a map of R modules. So I can also think of this as a map of R modules. Again, I'm just taking R to its pth power. I'm going to write its pth power over here as this thing, just notationally. Splits as a map of R modules. And what do I mean by that? So I just mean that I have a map back the other way that composes to be the identity on R. So yes.
Here's about the notation, you mean F star R. Right, for R to the P, you write F star R. Because there you write F star R to the P.
No, we send 1 to 1. So we send 1 to F lower star 1. So then if I think about it's an R module, now I'm thinking of it as a map of R modules. So I send R times 1 to R times F lower star 1, which is R to the F lower star of R to the P.
I think once the F lower star is being used just to signify a ring element and not applying the map.
Yeah, the F lower star is talking about like the elements in here as an R module. Well, or as a ring, either one. But in this case, I'm thinking of it as a map of R modules. And the R module structure is that acting on the outside with an element of R pulls into being Pth powers.
But this is just, so if you write F lower star R of P, this is R of P.
Yeah.
Yes.
Inside of R.
Yes. Yeah, sorry, the F lower star, okay, this notation is really kind of confusing, I'm saying. So F lower star is not something acting on elements. It is just notation to tell me that I'm in this module rather than this module. Yeah, the notation, I mean, so the notation has historically grown. Yeah, some people use this notation R to the 1 over P, in which case then we're thinking about Frobenius as just being the inclusion of R into those Pth roots. But I think, I don't know, I decided between the two notations and decided this one was more clear, but maybe it's not. But yeah, this is sending, I mean, this is still sending R to R to the P. If I think of it without the notation, this is just a copy of R with that special R module structure. Yeah. Yeah, the whole point of writing this notation is just so that I know which ones are module elements and which ones are like acting by elements of R using the R module structure. All right. Oh yeah, I should make an aside really quick. So F splitting, I think this is the easier definition to work with. But when we're F finite, it's and Noetherian, it's equivalent to something called F purity. So maybe I'll say a little bit about that. Maybe aside. F split, actually this holds generally implies what's called F pure. And I'll tell you what that is in a second. And the other direction works if R is F finite and Noetherian. Or Rm is complete local. Then I'll get both directions. So yeah, we're generally going to be in this case. So I might accidentally going to use these interchangeably, which is okay as long as we're at finite and Noetherian. But what is F purity? It is F pure if for every R module I look at the induced map. Applying this Frobenius, and these are, think of these as R modules tensor over R, and it has to be injective. Okay, but because I think this is a little bit harder to think about, at least during a talk, I'll focus on F splitting. Sometimes, well, anyway, yeah, maybe I'll just say that. Okay, and maybe some properties of F splitting I want to point out. Is the following theorem, which essentially is going to say, I don't need to check splitting on just a first power Frobenius. I can check it on any power Frobenius. The following are equivalent. So this map splits as a map of our modules. Or this splits for some E, or equivalently, it splits for every E. I can check it on any power. And this type of condition shows up a lot in singularities. Often it will be true that you can equivalently check for all or every power of Frobenius for different conditions. Oh, and maybe also another theorem. This is where maybe I need F finite. If R is F finite, oh, do I need Noetherian? I think maybe I should say Noetherian. Then R is F split. Also, F pure actually always works. If and only if R localized at P is F split. For all P in spec R. I could also check it locally. All right, and then another thing I want to note about F splitting is that there's this really useful criterion called Fetter's criterion, which we can use to check if something is F split. And maybe I better say, okay. So because this is a local property, I'm going to state this about local things, although I can also do standard graded. And let's do it for regular local. Cool. Maybe a finite. Or so I can think of S and M as regular local. This is the maximal ideal, or I can think of this as a standard graded polynomial ring with M being the homogeneous maximal ideal. Then I take any ideal in my ring, I can check whether or not S mod I is F split. So S mod I has F split if and only if. All right, so I'll explain the notation in a second. So I to the P to the E, maybe I should explain this now. So for any ideal J, let's say it's F1, Fn, this notation means I just raise all of my elements to the pth power and I take the new ideal that I get. So you can think of this as like the image of J under the Frobenius, the ETH Frobenius map. Okay. But what do I say? So if and only if the things that multiply I into this P to the ETH power have to not be contained in M to the P to the E. For some, it's actually equivalent to every 0. All right, and so maybe I should say this is things in S multiplying I into I to the P to the E. Okay, let's immediately just unwrap this in the case of hypersurfaces. So, question? If you take I to be 0, then S mod, I mean, it's already regular. Oh, maybe I should say, if you're regular local, you're going to be F split. So, in fact, it implies something stronger that we may or may not talk about at the very end. You'll also be what's called strongly F regular, which also implies F split. Yeah, so if you do that, oh, I see. Sorry, we want I to be non-zero. Yeah, because I guess, no, that's right. That's fine. Everything will multiply 0 into 0. So this will be the whole ring. So it will not be contained in this power of the maximal ideal in particular. So it will be F split. Yeah, it works. That's fine. But yeah, let's unwrap this in the case of just a single element. All right, so I is generated by this single element. Well, then this thing, well, I to the P to the E is just F to the ideal generated by F to the P to the E. And I is just F. So this is just F to the P to the E minus 1. So in this case, say S mod F is F split if and only if F to the P to the E minus 1 is not contained in this maximal ideal to the P to the E. And I can check it for any E I want. So I could just check it for E equals 1, for example. All right, let's do some examples of F split rings, and then we'll do some non-examples. So the polynomial ring, in fact, any regular ring should work. Any field K of characteristic P. What else can I do? I could take Veronese's. So think about just taking K adjoin the monomials of degree D in n variables. What else can I do? I could do Stanley-Reisner rings. Actually, it's not too hard to check like directly using Fetter's criterion. Oh, I should have said this is Fetter. Sorry. All right, we could do Stanley-Reisner rings. So the regularity is our ambient ring, and then we're allowed to quotient by anything.
Ah,
Yeah, so we're checking whether S mod I is F split. Yeah. If you're regular, then you're definitely F split. Can someone move over the? All right, and maybe I'm taking longer than I thought. All right, let me just do some examples where I can draw a picture. So we did Stanley-Reisner ring. So for example, draw a picture like this. Yeah, and I guess, okay, in this case, what I'm kind of thinking of is the standard graded case. So in the standard graded case, what I'm checking is sort of equivalent to F splitting at this maximal ideal. So it's going to tell us something about the singularity here.
Where's the standard part of the standard graded necessary?
Yeah, otherwise,
I mean, like.
oh yeah, and I guess
if it was a non-standard but still Z-graded ring.
I have to think about it. I don't think it works. Well, actually, I don't know. I have to think about it. So yeah, and I guess in the standard graded case, I want to take a homogeneous ideal.
Yeah.
I should have written that.
I was just curious if other.
Yeah, you can think about it. I think the way I've seen Fetter's criterion stated is just for standard graded or for this regular local, but maybe think about whether or not it works otherwise. In general, yeah, I mean, you could directly kind of use the sub-splitting definition and see whether or not non-standard graded works. All right, let's draw some other examples. Maybe if I think about this guy. Oh, I shouldn't write my axes. Okay, let's just draw the picture. I was kind of studying what's happening with this homogeneous maximal ideal again. Yeah, this guy is still F split if P is not 2. All right. And then maybe let's do, okay, one more example. So it can depend on the characteristic. So this is F split if the characteristic of P, the characteristic P is 1 mod 3. And not otherwise. And maybe let's just do a couple non-examples. Well, the other cases of this guy are not F split. And maybe also something like this guy. So this guy looks like this. This is not F split. Okay, so roughly what F splitting means, if at least if I'm thinking about the standard graded case, is it means that the singularity at the origin is mild enough, or maybe it's completely smooth. So here it was too bad to be F split. Okay, in the last 10 minutes, I want to talk a little bit about what we can say beyond F splitting. All right, and so for time's sake, I think I'm going to stick to the case of hypersurfaces, so just ideals generated by a single polynomial element. And maybe our question is, if we're not F split, can we somehow measure how far away we are from being F split? So consider maybe S in those same circumstances before, so either regular local or standard graded, and take an element in M. So note that, well, because of this, I definitely have that F to the P to the E is definitely contained in M to the P to the E. And so the biggest, so T equals P to the E minus 1 is the largest.
Like the only non-example of the shoe that the shoe like.
Oh, sorry, I should have said not.
Okay.
Then those are on.
The other side, that's
The only non-examples that I gave, yeah.
okay.
There's lots of other examples, but yeah. Yeah. Those are the only two non-examples on the blackboard, yes. So T is P to the E minus 1 is the largest value such that F to the T could possibly not be in this M to the P to the E. And we know by Fetter's criterion that we're F split exactly when F to the P to the E minus 1 is in M to the P, is not in M to the P to the E for every E. So maybe we can consider not just when this value is P to the E minus 1, but what value it could possibly be. So define the F here threshold. This is at the maximal ideal of F. Again, I'm in this regular local rank or standard graded ring. And so some people will call this the F here threshold of the pair S and F because I'm considering the ambient ring as well. But this is the supremum. Overall, values T over P to the E such that F to the T is not contained in M to the P to the E. And maybe one thing to note is that, all right, if my S mod F is F pure, then is F pure or F split. Yeah, we're going to be in the F finite case when I want to say both of them. But I guess I assumed it there. I guess it did. Yeah, okay, fine. So if it's F split, then this is just the soup of, so I always get P to the E minus 1 here because F to the P to the E minus 1 is not contained in P to the E. So I get 1. Okay, this is called the F here threshold. Of F, and it's kind of thinking about it at M. Yes, I do need the soup. Yeah, and maybe some comments about it. It's not clear, but it will be a rational number. Maybe I'll do some examples. So let's just go back to those examples. So let's do these. Okay, great. So here, these guys, from what we just said, is the F here threshold. If I think of these guys as F, all of them are 1. And now this is where things get a little bit interesting. Let's do this one because I have more room. All right, so in this case, the F here threshold is 1/2. 1p is 2. It's 2/3. 1p is 3. And it's 5/6. 1p is equivalent to 1 mod 6. And it's 5/6 minus 1 over 6p. 1p is 5 mod 6. Okay. So maybe I'll just say in the last like minute or so, that roughly, maybe I should just do this here. So in general, it's between 0 and 1. In fact, you could put 1 over the multiplicity of F or 1 over the degree if F is homogeneous here instead. That's not too hard to show, but and smaller F here threshold, let's put this at M, means in some sense worse singularities. At this origin. Okay, and what I was going to say that I didn't have time to say is that this is actually really analogous to a characteristic 0 measure of singularity called the log canonical threshold. So in general, it's a lower bound for what's called the log canonical threshold. And if I take something defined in characteristic 0 and I do some sort of reduction mod p, and I take a limit over all p's, I'll get exactly the log canonical threshold, but this thing can generally be much lower. So I was going to tell you more about log canonical threshold, but I think for time I should end here. No, in characteristic 2, oh yeah, right. Sorry. Well, yeah, so I guess it is 1 when p is not 2. In characteristic 2, it's 1/2.
Sorry, what was the question? Oh, what is the F pure
The
threshold?
question was that middle example there. It says what's the F here threshold, because I wrote when p is not 2. So of that nodal curve there, yeah, so in characteristic 2, the F here threshold is 1/2. But otherwise in characteristic not 2, the F here threshold is 1. So yeah, there's somehow this is saying that the singularity is worse in characteristic 2. Yeah.
Can people
Oh,
assume
if
get
you
that
take that a-
question, or
Not at all.
Oh, sorry.
pass
Okay.
the mic so that it can be heard. You guys super close.
So for that equation, you take you add 1,
Yeah.
then there's no singularity at the origin. You just get an elliptic curve, nothing elliptic curve. But it still fails to be F split in characteristic 2. So
So yeah, I kind of brushed under the rug with this, but F here threshold, if I want to measure F here threshold at a homogeneous maximal ideal, I have to take F contained in that homogeneous maximal ideal. So it has to be, you have to measure, essentially geometrically, you have to measure the F here threshold at a point on your curve. So if you want, you can move your curve around like any point to the origin, and then take that here, then you can take this exact definition. But yeah, if I just add 1 to that equation, then I don't want to consider, I mean, there is no definition for that pure threshold at the homogeneous maximal ideal since it's not contained in the homogeneous maximal ideal. Yeah, so, oh yeah, I should say I is contained in M. Yeah, I guess my problem was I wrote regular local and then just wrote standard graded. But yeah, the point is I want a homogeneous ideal in the case where I'm in standard graded. Otherwise, regular local, I guess I is always contained in M. Yeah, these are all the standard graded example. It's S is the ambient ring, and then you're quotienting by something. That's true. Okay, so I can do, I mean, I can, so it doesn't need to be, I guess, if I just have a single element, I can just check whether or not it's in the maximal ideal. That's enough. That's fine.
I just wanted one clarification. The P congruent 5 modulo 6, what is the pure threshold there? Is it 5/6?
5 minus 1/6 times P. Sorry, 5/6 minus 1/6 times P. Yeah, so it's close to 5/6.
And then just in general, is this Fedor's criterion what is actually used in practice a lot of the times to prove?
Yes. Yeah, I think this is like the most useful tool for checking F splitting. Yeah.
Maybe this is good. So when you do singularities, for me, the first two singularities look very similar, right? If they're localized
Yes.
and complete, they're the same.
Yes.
But that does change the F pure threshold, and this is complete.
Only in characteristic 2, but otherwise, no. I mean, so in in this example. So I guess
Okay, but
if you took a limit as P goes to infinity or something, then what your intuition would maybe match up. Because then in fact it should be the same as long.
characteristic completion changes.
Yeah, so depending on the characteristic, it can be, yeah, it can distinguish between those two pictures.
So, wait. So the F pure threshold is in the case where S is a regular local, we have is 1 if and only if F over I if F split, right?
Yes.
But is it defined also like for not regular, and can it be 1 and think not be F split in that case, or is it just like defined only for that case?
Let's see. So if I define, so I guess this is the problem because I only defined it for hypersurfaces in regular local rings. So there's 2 definitions you can work with. One is called the F threshold and one is called the F pure threshold, and they match up when your ambient ring is regular local or standard graded. So wait, sorry, what was your question again about this?
So like that is defined only for the regular local, so I cannot define that for just a local ring.
Well, no, you can define it in general, but this definition like requires that setting. And it also like I've only given it for a hypersurface, but yeah, you can extend this definition. I mean, so if you do the kind of natural extension of this definition, then it's called what's called the F threshold. So if you do the like, so if you do something like this, yeah, I mean, I guess you want to be talking about it at some local point though. So, but if you just do this soup of T over P to the E, such that A to the T is not contained in M to the P to the E. This is something that's in general called an F threshold, but will be an F pure threshold when S is regular local. But yeah, anyway, your question, you do get 1 if and only if this thing is F pure. Otherwise, yeah, this doesn't hold with this definition if the ambient ring isn't regular local. But there is a way to define an F pure threshold in that case.
Okay.
Yeah.
And the other question, can you repeat why we can take F that is not homogeneous, and like if the F pure threshold that comes in the example, F is Y to the second minus X to the 3, right?
Yeah, so you don't, okay, so I guess I should have said, yeah, I guess I defined it this way. You only really need that F is in the maximal ideal to be able to define this. I guess my definition here, you only need to check if it's in the, like, you just need it to be defined at the point 0, 0 to be talking about the singularity there. Yeah, so the definition, maybe what I said was confusing early on. I don't need if I'm thinking about hypersurfaces, I don't need the hypersurface to be homogeneous, although we will often care about that case, but I don't need it to be homogeneous just to define a pure threshold and compute it. But yeah, I definitely do need I to be contained in the maximal ideal in all cases. Otherwise, I don't want to be studying a singularity at a point not contained in the ideal.
What is the criterion for a toric variety to be F-split?
In general, I don't, off the top of my head, I don't know a good criterion. So maybe I won't say, I don't know. But there might be something that I just am not thinking of at the moment, but at the top of my head, I don't have a good criterion.
Criteria for that. So for vector toric varieties, there is a criterion for them to be F-split, but this goes down to the third diagonal or something.
Okay.
So because that's important for various applications. This implies many things. This is by Sam Payne, and it's
Okay.
a lattice polytope criterion that only depends on the set of rays.
Yeah, so look up, yeah, I don't know the criterion off the top of my head, but apparently there is one by Sam Payne
So I
in
think that
some cases.
this Frobenius split is kind of often or something. But there's a like go down to the third diagonal, then there's a combinatorial criterion for that. There's a paper about it.
Great, thanks.
Are there any other questions, including on Zoom?
Oh, there's stuff in the chat. Is that? Maybe that's just that.
No questions. Yeah, just other things.
Okay, great.
Okay, let's thank Janet again.